Okay, so just a quick summary. I will upload more tutorials next Wednesday or have a review session plus office hours next Wednesday before the test. This week is pretty busy, so just email me and I'll get back to you as soon as I can. So, I had discussion this morning, and discussion is canceled this Friday because I have to study, but I will make up for it next Wednesday. And I'm posting this video too, and I made a bunch of notes. So, to address the questions from this morning, I only posted my recent notes because there were questions this morning, so now I'm addressing it. So I had a question on question 7. Professor is probably going to go over this tomorrow during lecture, but just to clarify, I had already added these notes for question 7, but I added more this morning and right now. So this is what we went over. I'll add the discussion video recording after this little quick recap, and I also have a transcript in case you can't understand or I was going too slow. It's just more organized. I just listed out what was said and added some clarification. Okay, so for question 7, I had a couple questions from students and they were confused about the order of the equations, the scenarios, pump problems in general. Professor said there's going to be a centrifugal pump on the final, so I just added some notes to help you and some video YouTube suggestions. If it's not me and I'm not helpful, I recommend these other videos because I can't show you everything. But um, so for this instance, we have radial entry, and I just added these clarifications. So also students were confused on lecture 15, where these equations came from, the highlighted ones. So I only derived them because it was requested by the student. They were confused where these equations magically came from or why are they connected, and it was not gone over in depth apparently, but these drawings look really beautiful and I added more notes. So this is for Q, and there was also confusion on A. So for this problem, we have the impeller width, which is B. I just labeled it B because to some pump problems, they label the width of the impeller like A, B, whatever you want, whatever works. You could call this A. Oops. But if that's confusing for area, then that's why I just chose B. And this is not the surface area. A student was asking me about that. So Q is normally, yes, surface area, cross-sectional flow area at the inlet times the normal velocity. And then A would equal 2 pi r times the blade width, okay? The impeller width. So this is the equation used. These notes are posted. I just didn't include the lecture slides in my notes that I am going to show right now, that I have right here. I just added them. I don't know if you want me to post that, but I'm just referencing lecture 15. So maybe you could do that on your own. Okay, so this goes over the full derivation since there was confusion on A and B. Okay, so continuing, I plug it in, get that equation. Those are what the variables represent. So it's not surface area, it's the impeller blade thickness. Okay, and then this is the derivation for the Q equation. And that's from uh, lecture 15. Okay, so it matches up to what professor has. So this is the performance parameter Q. Okay, so just continuing. and this is the velocity triangle analysis. Okay, so there were questions about the order of the calculations. If you have a radial entry or just pumps in general, how do you know what velocity to use? What order do you go? So I described that it depends on the entry, the type of entry, and what type of pump. If the entry isn't given, it'll tell you what kind of pump it is, but you're given the entry is radial. Assume radial entry, so you're fine. And you're given the impeller thickness, the width, sorry. Okay, and you're given the rotational omega and both of the beta angles, which is generous. Okay, great. So it also mainly depends on the velocity triangle. Those are to help you understand the physical aspects, to picture the and visualize the problem, the concepts of the angle, which angle is most effect is giving that power. Okay, so and the velocity. So these are just the breakdown of professors of velocity triangles because students were confused and why we're involving tangent, but we don't look at the tangential velocity at first. Okay. Okay, so just breaking it up and deriving how that cotangent comes into play for the H equation, but we're not there yet, so let me know if you have any questions. And this ratio is due to the mass conservation, the continuity equation, because I wrote it, where is, I don't know if I posted this, but it's here, okay. I posted a different version, but if you want me to post this, I can. So this is the relationship between the inlet and outlet normals. It's maintained by mass conservation. The second normal velocity u n2 is influenced by u n1. That's why we have this ratio. And to find u theta 2, we look at the outlet based on the blade angle beta 2. And q is set by the radial entry condition and calculated using tangent 40 degrees. So this is just a derivation of the actual equations over here, and this is how we use them in a problem. Okay, so continuing, we have the conservation of angular momentum used to find torque. So then we plug in using the velocity triangle variables right here. Tangential velocity components of the inlet and outlet and the radii, okay, of the impeller. Then to find power, we plug it in, and this is the final equation. Okay. And then I also showed how to find the final H equation from the Euler equation. So I derived the Euler equation, and then I showed you how to find the final H equation for the parameter. Okay, so then we can get this version, or we can just rewrite it in terms of Q. So I showed both ways if you see in textbook or whatever, or if you're just doing it on your own, or if you don't, they're just there to see. And then matches professor's slide right here in terms of Q. Okay, and I just answer some questions right there, and then I included this slides from his lecture 15 that reference what I am deriving. Okay, so I can upload the annotated version of these notes soon. Okay, and I just added these lecture slides from lecture 15, so it's after the centrifugal pump notes. Okay, so I just added all those slides. I can post this, or you can just go look at it. I just added a guide to approach pump problems since that's what the students were asking me, and it just depends on the velocity triangle, drawing it right, or the type of entry that you're given, and if you're not given the type of pump, but ask professor how he's going to give it to you, the problem. I think it might be like this, where he'll tell you assume radial entry, assume it's typically just radial or axial, and if it's centrifugal, it's probably going to be like this. Assume radial entry unless stated otherwise. If pump is centrifugal, okay. Okay. Okay, I just defined more terms and concepts, the inlet versus outlet exit. And then this is a flow chart. Okay. I added more notes to how to solve question 7. So from this morning, there were a couple questions on concepts, the order of calculations. So I added that to this new version that I have posted. So I basically just added some more concepts as you go along the problem and broke down more of the equations. Okay. So I made the connections and I didn't really skip steps, but let me know if it's still confusing. Okay. Seven. Did Professor go over number 7?
He's gonna go over all of it on, or like, you mean like the content, right? I mean, he did cover the concept. He didn't cover this mock final. He's gonna do it on Wednesday.
Oh, okay. That's tomorrow. Okay, okay. Okay, so question 7. What did you have a question about?
Yeah. When I was going for question 7, I just had basically trouble finding out like when to use the velocity, like the normal velocity and the tangential, or not the tangential, sure, tangential actually.
You mean you couldn't picture it?
No, I was able to like figure out how the arrows work now because after we went over it last week. But it's mostly just like, oh, we're supposed to find like this specific thing, and then we're eventually gonna get to that answer. So, for example, like we have the L in and the L out. That would use the normal, I think, the normal velocity or tangential velocity, right?
For the momentum, ln.
Like ln would use the tangential velocity, and then the mass flow rate would use the normal velocity. So I'm just thinking, like, is there a way? Could you help clarify it?
For the momentum balance, it's usually tangential, you said?
Yeah, just in simple terms, how do we know when to use the normal velocity and the tangential velocity?
Oh, okay. It depends on what you're trying to find, and it'll tell you what kind of pump it is. So this time we have a centrifugal pump, so it's different, and it'll tell you what direction, if axial versus radial. So then that changes the angle. That's a big tip. Okay, and then also depending how you draw your velocity triangle. So that is another reason why setting up the problem is most of the work. Once you visualize it, you're able to once you visualize it and you look at it with the right angle, you're fine. You should just set up your equations based on your velocity triangle. It's supposed to help you picture but if you don't draw it right, then yeah, it ruins your work. Does that make sense?
I think I may be a little bit confused still.
Oh.
Like I know, like, so, like, how do we, like, so, like, I guess,
You want me to give you a couple examples?
yeah, that would be very helpful.
Okay, let me see. I could post it too, versus just doing it on the spot. Let me see. So you want to see different cases where you use where you're trying to find the tangent versus like cosine or sine?
Oh no, like the velocity of that's tangential and the velocity that's normal. Like when do I
Normal.
use each specific one? Like in for example, like in 7.1
Uh-huh.
for that problem, we would find like, oh, since we're finding the velocity or the mass flow rate of the inlet, we know that like we'll eventually have to find that the Q is equal to A times the velocity. But how do we know which velocity to use?
Okay. So in this case, we're using the normal for 7.1, and it says in the problem, that's what I was trying to imply, that it's radial entry. So we're using the normal, but that's also equal to the tangent. So it depends how you view the triangle, because it's kind of lopsided, and there's another one here. So you go off of, you're trying to find for the first one, so you look at this triangle, and then so this one, and then you can solve it by getting the tangent of beta 1 to get the normal, because the normal is just pointing up. You don't really have an angle for it. So then you use the angle for beta, which is the tangent. So tangent 40 radius 1 omega was equal to the, sorry. Does that make sense?
Yeah, that makes a lot of sense.
Okay, I'll keep going.
Okay. So what if instead, if our assumption was changed, instead of assume radial entry, we say assume tangential velocity, then it's tangential instead.
Assuming what?
If it says assume tangential entry, then it would be UT, and then we would just do that.
Usually in the pump problems, it'll tell you it's radial entry or axial. Those are the two common entries. So it depends. Centrifugal, sometimes it won't tell you, depends on the problem, but sometimes normally it does, but sometimes it won't. And but I don't want to confuse you, because we are given, in this case, let me see. Oh yeah, it doesn't tell you. So, oh, it says right here, assume, there we go. I was like, I'm pretty sure it does tell you. Yeah. Okay, so sometimes it doesn't tell you, but sometimes it can. So in your luck, you are told. But typical cases, it's radial entry, axial entry. It's not really tangential entry, but if you did have that, then you would have to draw your velocity triangle and figure out your view. And maybe, did he go over velocity triangles?
I think very briefly.
Okay, because I told him that you guys wanted more review on that, so I think he's gonna go over it. And he said he'll do the problems I don't cover in class. So maybe I could have more office hours the Wednesday before the exam. If needed, I'll post that. It can be Zoom
or in person. I could have my office hours today over Zoom, different time, if needed, because I don't know if the time works today for people. It's at 12:30, so we could post a couple different examples of different velocity triangles. Yeah. Okay. So yeah, it just depends how you set up the problem. Based on your velocity triangle, you're going to do your calculations. It's supposed to help you guide to view the problem, how it's working. So professor drew these, and I gave, in the solutions he posted, so he gave it to you. And you can ask him for further clarification on the velocity triangles. I'll try to post examples, but he's the best source. So in this case, it's radial entry. So let me see. I have this saved. Wait. Okay. Sorry. Yeah, 7's a good problem. I didn't really find it in the textbook, so I would ask professor for, but I'll post more clarification and try to answer it right now. Let me see. Okay. So then, for once you use the normal U N1 for the first 7.1, 7.2, it's asking for the power required to drive the pump. So we use the normal that we calculated, but now we're using theta 2 because that's the main angle that gives us that power, that drives the power required to drive the pump. So you want to know like how to know which velocity to use for each situation? Yeah. Okay, that's a good question. Okay, so the radial entry means that it's perpendicular to the impeller blade. So okay. Okay, so if it wasn't radial, we would need to account for an initial tangential component. But since we don't have an initial tangential component, we first look at the normal and then we relate it to the tangent. So I'll add some notes on that so I don't confuse you. Okay. Does that make sense? No? Almost? Okay. Okay. So then, what's confusing?
I guess like when we're finding some points, we would start off by writing or we first, since we have the maximum rate of the initial one, we knew that the in and out would be the same because nothing is left there. And then when we found the velocity of the normal one for 2, so since we have 1, we can relate to 2 because of we have the angles and we have pretty much everything there. And then once we find the tangential for that, like how do we know that when we set in L in L out, that it would be UT? Because when the control volume, so the control volume is like the line, basically like the line area. So wouldn't it be like L out would be like straight out?
Oh.
Because I know it curves and then it kind of exits.
So you keep saying L in, L out. Were you using momentum?
Oh, that's momentum, yeah.
Well, I was in the equations. I don't use that. So maybe get out of that mindset for this problem. If you can apply it, then great. But so far you're getting confused. So think of it as flow rate and the type of entry and velocity triangles are supposed to help you, and then the power, the literal sense of like what's going to actually give the pump power, like which angle or like which scenario would actually give the pump power. The most important like angle is going to be the one you're calculating, obviously, that gives the pump power. So you use 7.1 to get 7.2. Where is it? Sorry. Oh, right here. Okay. So you finally get your answer right here, but you had to use both components. So UN1 was found right here, and then UN2, we used the ratio of the radiuses and UN1, so we needed to find UN1 first. Okay.
Oh yeah, just to check.
Yeah.
For the volumetric flow rate, the A, so like the A area times the velocity, that area is the surface area, right?
The DA?
So like the Q is the 2 pi r times the B. So that's supposed to be the surface area, right?
Oh, let me
Or
see.
circumference. I mean, it's the circumference, but some volume, so I know that, but.
Oh, okay.
Think, like what specifically?
That's
it's just all of them are not. They're all A. Like the cross section is A. This is also A.
yeah.
So
Maybe.
like AS means surface area, and then like AC is like cross section.
Yeah, I could fix that. Let me see.
Yeah, he just gives all of them as A for his.
Sorry, maybe that was a typo. Let me see. Oh, impeller width. So, is it said in the problem? Let me see.
This time it didn't say.
4.75. Oh, right here. So yeah, he uses A, I use B, whatever is fine. It's just it's implying the same value. So if that confuses you, I could just go back to what professor uses, which is A. Is that fine?
Oh no, I'm perfectly fine with how the formula is just used. It's just like I'm just not sure like the 2 pi or 2 pi times the r times the b. What is that? That's a surface area, right?
Oh yes. Okay. So the impeller width, the impeller is what's driving the flow, and that's where the radial entry, it enters the impeller perpendicular to the impeller blade. So that's why we need to use the impeller, what is it? impeller width, and it's considered the surface area. Yeah, I could expand on that. I'll add better notes. Okay.
No, it's just his notes are all A, so it's just like
Okay.
sometimes it's A, sometimes the other A.
Oh, I see what you're saying, like that, like capital A versus lowercase a.
No, it's just straight up. They're all A.
Oh yeah.
So area, like if you do Bernoulli's equation, you know that area times velocity equals area to cross section ones.
Okay.
Those are A's. This is also A.
Oh,
so
I
you're gonna
see.
have to guess, and then like you just mysteriously get 2 pi r times the thickness versus the like area, which is pi r squared.
Okay, that makes sense.
It doesn't make it clear whatsoever.
Okay. I did define B in the beginning, but that does make sense. I didn't really define this relationship, so yeah, I could add another equation. So okay. So then we look at theta 2, and we use it. We find it using both calculations, U and the normal 1 and 2, the first and second normal. Okay. So then, yes, we apply the angular momentum conservation right here. Sorry if I was saying not to. You were just using it for like the whole problem. I would use it like not literally like L in, L out too much, like guess overall, but like not formula wise. You know what I mean? Does that make sense? Because you kept saying L in, L out, like.
Yeah, you kind of just like initialize it later or like sometime. And I guess now could also work too.
Oh, so you wanna be consistent and apply that equation?
For the most part, I think all of them are applied like that.
Oh, okay. I just thought you were getting confused, like.
No, I know what. So I know what the values are supposed to be. It's just like you're gonna also have to. It's another guessing game basically, like how the area and cross section, surface area and cross section area, they're both A. All these are all U. So like they're either tangential or they're radial.
Oh, okay.
So it's just another guessing game basically, unless there's some way to figure out exactly, which in this case.
Well, that's what the velocity triangle's for. It shows you the view of the problem, the entry, the flow, and which velocity to use based on the velocity triangle. That's what it's supposed to help. I also struggled with understanding the velocity triangles. So what helped was looking at the problems in a literal sense of like what is going to give what angle and what's driving, what's giving power.
Yeah, so since it's the power in this case would be the omega, so we know that it has to be in that direction. Is that the best way to put it?
Yeah, so that's why we need so we're looking at both normals, and we need to account for both of them when we're finding theta 2, which is right here. Okay, because it's driving, and then omega is going like this, so it's going, and then let's see, beta 1, beta 2. Okay, so this is blade 1 angle, and this is the second. Over here. Oops. Okay. Okay, so the impeller rotates and pumps water. So yes, you will need omega because it's rotating. So we have this big momentum arm, R2, which is used in the calculation. And R1 was used in the ratio, but R2 is the main driver for the omega. Okay. And then we use the second normal for the calculation of theta 2. It's in the same velocity triangle if you want to think of it like that. Okay, so where is it? I circled it already. Okay. So this is basically turning it. Okay. And then once we have u theta 2, we're able to use the previous calculation 7.1 to find the torque. And then we times it by omega to find the power. Any questions? So for theta 2, we are looking at the outlet, and that's why we use beta 2. So that's why we used for R2, we're using R2. That's why we're using R2 because that's the outlet. So I use 0.105, which is given as 10.5 centimeters. So we're looking at the outlet for the power because that's the final step. The outlet is going to drive that power. So let me write that. Okay. Okay. And the second normal velocity is influenced by the first normal velocity from 7.1. That's why we have this ratio. Okay, so key connection. Let me write it over here. I'm running out of space. So the normal velocity at the inlet, I think I defined it like that. Let me see. I could fix that. Yeah, velocity triangle analysis at the inlet was theta 1, and then the normal is un1, but I'll write it again. So the normal velocity, repeating it helps, the inlet, aka un1, determines the mass flow rate. That's why we first calculate that. Does that help?
Yeah. That
Okay.
makes sense, yeah.
Yeah? Okay.
Because it enters radial entry, so
Yep.
that's the reason.
Okay. And that same mass flow. Oops. Okay, and then Q for 7.1. Here, let me erase this. I'm running out of space. Let me. Ah, okay. Okay, I'll post this after, but I'm also recording, if that helps. Since it was raining, I'm pretty sure not everyone can make it. I did offer to do this at a different time, but nobody told me anything. Okay. And then I can have office hours next Wednesday before the test, if needed. Okay. Let me just fix this real quick. I'll go faster. Okay. Awesome. Okay, so Q is set by the radial entry condition calculated and then 7.2, this is 7.1, uses the outlet velocity to compute the torque, requiring the second normal velocity, which is derived from the first normal velocity in 7.1 because it's influenced as a relationship. And this relationship, this ratio, okay, is maintained by the mass conservation. So it's all connected. Because it's all one pump, it's all connected, so that's why you interchange. Does that make sense? Because you asked me to like show you the order, and it's like you have to see what's connected and the velocity triangle.
Is there a way to just specifically jump to the fact that, like, since we know that this thing is rotating at a fixed, or with a fixed omega, then that means that it's only in the tangential direction and not the radial direction, and that's why we can, so we have to solve for the power basically only in the tangential direction. We just jump to that conclusion.
It depends on, because if your pump is angled, it depends on like what you're given for the problem, like the pump, the velocity triangle. Well, yeah, you could say that. Sometimes there were cases where it's like, yeah, it's gonna be the tangent because we're looking at radial. Yeah, you could do that. But sometimes the velocity triangle would be curved or different or rotated, so then it would change things. You know what I mean?
Yeah.
But I could get more clarity on that. And then professor is the best source, but I'll try to answer that better.
Yeah, because if we could jump to that we need to know is, okay, well, now that we know that, then the exit has to be basically the sum of what the power is minus the velocity that's going the opposite way.
Yeah.
You can easily solve for it like that.
I remember that. I used to, when it was radial, that meant it would be this, yeah. Okay, you want the fast track?
Well, I mean, I don't think you gave us that much time last time. Yeah. So like any time would be great. Like I mean, I can sit here all day and understand the concept. But if I don't solve it, write it down for this right in grade, then
Yeah, of course, of course.
yeah.
That makes sense.
Also, could you quickly go over the 7.3 about like that pump head equation and how we can make the graph, the pump curve?
Oh, okay.
Yeah, because I know that one is like a formula. We were just given that formula in the slide, and then like some derivation where it's like q over 2 pi or something to find like the slope.
Okay, so if you see that your Q is small and your shutoff head is big compared to that value, that's why you're going to have this relationship with the graph. That's just like a pretty clear indication.
Yeah.
Just look at the values, compare them. So it's like opposite, it's going to go down because as Q like is going to 0, it's close to 0, and it just has an indirect relationship. And
so we were given this formula that like the pump head is like 1 over g times, or 1 over g times like the difference between the entry of the exit versus the entry. So
is it exit minus entry?
yeah.
Oh, okay, I think I remember that.
I'm not really sure. He just kind of explained it one slide and then quickly skipped it or quickly just went over it because we had to go to like the next lecture because the class was over at that time.
Okay, don't overcomplicate this. It's the pump curve is pretty simple. Once you calculate your values, you're able to see the relationship. So you could just draw a simple graph showing like the relationship between them, and then that formula, you could ask him if he wants you to use that to derive the curve, or if
He definitely will. I can tell you that. It was in the solutions too.
Oh, wait, let me see.
Like we're just given directly that formula, and then later on there's a second formula that's also even more confusing. But I looked in the lecture slides. It just popped on there, and that's it.
Well, where is where's the
right
equation?
Right underneath the 7.3, 7.4 around that area. Yeah, right there. It just plopped in there.
Oh, you're asking me to derive this?
Or no, like just quickly, like I know it's 1 over g times some value. Is that some value just the entry minus or exit minus the entry always, right?
Well, yeah, it also makes sense. Plus, I was showing that in my solution that it's outlet minus entry. Where is it?
And then yeah.
Where'd it go? Yeah, so outlet minus entry is usually the order.
Yeah, because if we saw it like the previous way, like we did before with the L and L out, then it wouldn't have that issue, wouldn't have that thing.
Yeah, that's why that's the wrong mindset.
Okay, I see. And 7.4 also has a pump entry, except now it's in a different form. So we just had no fucking clue how it was like that. Just kind of just like the omega squared times r2 squared over g minus the omega cotangent.
Oh, so I'm using the same formula he is technically. Yeah. I just wrote it a little cleaner, maybe.
Later on, the next problem right underneath. Like the first problem was fine. Okay, the rest was perfectly okay. 7.3, 7.4. You need to find the slope basically.
I see.
You have to like convert it in some way to have q.
I remember now. Okay.
All I know is in the slides there was something q over 2 pi equals some kind of formula.
Which lecture?
Lecture 15.
15. Do I have that?
Back to find it.
Oh, I don't have it.
It's like at the very end of the slides.
Did he this was the last slide he had?
I think very close to the last slide he had. I think like the second or third last slide, like at the very last one, at the very end.
I thought he did lecture 16 last.
Oh yeah, he did. His lecture 15 was last week.
Oh.
Yeah, he quickly went over it and then just like off you go. Yeah, it's there. It's there at the bottom. Like.
Okay, let me just post it on the side.
Yeah.
I think I remember that. Oh, this is a pretty good.
Yeah, that's fun. Yeah, right there. See, like number 2, and then just like it's just there.
Okay, I think I remember this now.
Yeah, it's just that entire part you went over in like a minute or two. Yeah, and then
This
you
is
skipped and this is onwards to the next one, and then like, and then, oh look, there's the pump curve. Oh, that's time for Naomi Stokes.
this is a Christmas Wonderland right here. Okay.
Yeah, I don't even know at this point.
These drawings are really nice though.
Yeah,
Okay.
I like this one. Yeah. It's just that he went extremely quickly.
Okay, I could, well, I'm recording, so I don't know if he watches, but I could tell him.
But yeah, see, like, right there, we were given that H just right then, and then.
The what? H?
Yeah, H equals 1 over G, the Q, T2.
Okay.
Yeah, right
Yeah,
there.
I used
That's
that formula.
That just randomly appeared, and then minus 4 is equal to that, okay, you cancel, and then the next one, oh, it just became a form of Q just because. Like, you see the Q equals 2 pi r b times the U and 1. And
Okay.
then, like, simplify it around.
Okay, so you want a derivation for that. I use this equation too. I just wrote it slightly differently for H. So that's fine. And then Q, so he just divided, once you find H. This equation.
So we just, I mean, he allows us to write out on a formula sheet. I mean, we can always just write it directly and then
Yeah.
have that, but.
I would write this formula,
Okay, well.
but small since it's probably just one little part to a question.
He's probably gonna give us centrifugal pump. It's almost guaranteed.
Why? Because it keeps going over it?
He said it will be on the file.
Oh, okay.
So
I don't know.
It's pretty much there. I would expect it to be like, oh, okay, what's the absolute velocity, and then for like that, and then find the power, and then find the pump curve, obviously.
Okay, I can give.
I would assume it'd be something like that.
Okay, I can. So you want me to derive those two equations?
No, it's just like how can we quickly find, like, okay, we're given this H, like, I know we could do this plug-in substitute stuff, but like bare bones, we need to use this formula. Like, how fast can we just do it? Because this shouldn't take that long. I know that for sure because of the Q, because we just have to find in the slope form of Q.
But are you saying like what variables we need to find?
No, not specifically. It's just like, oh, so this Q, oh, we have 2 pi R1 and V1. So like, okay, well that's nice. But
you're asking how.
Why wouldn't it be R2 or like?
Yeah, you're asking me to derive it, then you're asking me to explain it.
I just plug this. Okay, well I guess yeah. It's just, maybe I'm getting a little bit
lost.
here.
So.
Yeah, it's just like, oh, yeah, this is going straight into there, but later on it just became like an absolute mess. Like you can see, like the equation right above all this like over tangent beta 1, it just became that when it became a very simple.
Oh, right here. Like this.
Yeah. See, look, the one above is what we had before, and then it just became that.
Okay.
So like that just very quickly became extremely messy.
Okay.
I'm gonna have to review that slide.
Okay, I can add more clarity. And then I have office hours today. I don't know if I should make them on Zoom because it's raining. And or change the time, or if I need to change the time for people.
Also,
What time?
What time for
Office hours.
office hours? I mean, I don't really have time today.
Okay.
I mean, regardless, I definitely have time next week on Wednesday if you host it.
Yeah. Okay.
Yeah, but this
Maybe.
week, no. I'm pretty busy. Like really busy.
I'm busy too, so I wonder
Yeah.
if I could just move it to next Wednesday.
Yeah, if you move it to next Wednesday, it will be very helpful.
Yeah?
Last minute questions.
Yeah,
I'll just post some notes and then this video this week, and then next week I'll have my office hours.
do you have a discussion on Friday as well, or?
No, I canceled it for this is because I have to study, and then I was gonna post a video instead.
Yeah, that's okay.
The
But-
video, I think because you can watch that anytime.
Yeah. That's
Exactly.
true.
That's what I was trying to tell Professor. Because people were complaining about the time, the 8 a.m. And I asked what time they want instead, but nobody told me anything. So I don't know what else to do. But people have been starting to watch my videos finally. I spent a long time
Yeah,
on
because
them.
everyone knows they're gonna be cooked in a week, of course.
Yeah, they barely started watching them because at first it was like nothing, and I spent like a lot of time on them, so I didn't really want to do them. But then the students were starting to ask me like, "Oh, can you make one?" I'm like, "What?
Yeah.
You don't even watch them?"
I realize, wow, this final's really coming up. Maybe that's what's happening.
Okay.
Yeah. Also, could you just like at
What?
the very end, like maybe at the very end of this, the notes, could you maybe also like quickly write what assumptions we need to know for Navier Stokes? Because I know like there's a lot of minor assumptions like, oh, if it's
All of these.
or unidirectional or like something. I know we have to make those assumptions later on. Yeah, like there's a lot of assumptions to remember. And obviously, I think at this point he's just asking us, oh, just write it down on a piece of paper. And then we do it. I'm pretty sure he wants us to do that.
Oh my god. Okay, so I can move my office hours to next Wednesday.
Yeah, because I know it's just like a lot of work, and everyone would definitely appreciate. Oh,
Last
what
minute.
we need to know.
Yeah. Okay.
Like Navier Stokes just like unidirectional. Was it uniform one of them? Actually, uniform might be one of them. Steady state, obviously. Something like that. I know in question A was asking these assumptions, although these are like very little from what they asked.
Okay. I can post. I don't have time this week either, so I can add like a 5-minute video quickly explaining this, and then let me see. Okay.
I think would it be possible to go through like just going through an example? Like a
Yeah,
walkthrough?
that's what I'm thinking.
Yeah, that would
but
help.
but I don't know if I have time to post that this week. Let me see.
I would think like, or example-wise, maybe depending on what question it is. Like, I think you won't even need a video if it was a Navier-Stokes equation, because like those are just canceling. You literally on that, even on this mock final, you just cross out terms. Literally just.
So notes are fine for the Navier-Stokes?
Navier's, yeah. All we need is like, oh, we know that okay, if it was bidirectional, then that means like the velocity in this direction. Like in this case, it was xz.
So for the pumps, you want a video? Pump examples.
Yeah, it would be a lot.
There we go. That's more clear. Okay.
Yeah. And I mean, centrifugal pump in general, I think the cars would be
Okay.
pretty annoying in itself.
So centrifugal will for sure be on the exam.
Yep. Navier-Stokes will be a cross-out equation, like very similar to almost exactly.
He's gonna have a lot of office hours. Did he tell you?
Yeah, I went to his office hours yesterday.
Did it help?
He didn't really have a lot of time. I mean.
Well, he said he's gonna have like 2-hour office hours, right?
Well.
Like
he
this
has
Thursday?
2 TAs hosting office hours. He has office hours on Monday from 3 to 4, which I already went to yesterday.
No, I thought he said he was gonna have more office hours, like extra office hours this week.
He never told us about it.
Really? Oh, maybe he got busy. Okay. Okay. So this video has been recording for 50 minutes. So I will post this. This is easy for me to post. I could try to add a 5-minute extra explanation for like all your questions, and then the pump video. I don't know how long that'll take me, so I could for sure post it Wednesday, but that's last minute. But Wednesday morning maybe. But or I could at least post the notes for sure, and then do like a quick like 5-minute video. I could do that if I had to post it this week and add it. I could do that separate to this video. Yeah. Okay. Plus it'll keep it organized. Like, okay, this was discussion and questions, and then this is an extra pump problem. Okay.
I mean, the good news is that I don't think anyone is really worried about this at the moment because everyone's worried about that Thursday MATLAB final. Thursday. It's Thursday.
Thankfully, I'm
Thursday 11:59 to Friday 11:59.
What?
Yeah.
Everyone is focused on that.
Thursday.
So you have some time. You have some leeway.
Thank you for that. There's a MATLAB final Thursday.
MATLAB final, it is online, but it is going to be evil. Let's just say that.
Oh,
Wait, are you
yeah.
talking about
Yeah, he
18B?
posted exactly what it has to be too.
18B?
118.
118? Oh.
Yeah, that's why maybe they're watching the video just to get some general knowledge, but I think a lot of people are gonna send you messages right after that. It's going to be.
That is so funny.
you're
Thanks for
going to
that
be
tip.
that.
Thank you for the tip. So for sure, next Wednesday. Thank you, because I don't really have time this week.
Yeah, you have some leeway.
Thank you. I appreciate that. All right. Any other questions or any tips you want or?
I think for the Navier strokes, notes
So-
work. Stokes.
Yeah.
Do you have like a nice is there a YouTube video recommendation? You can just
Yes, I did. I said I had a recommendation. I just didn't post it. I forgot to. Okay, thank you.
I think that would be better, or not
'Cause,
better, but it'll
yeah.
help you out with like.
Thank
time.
you. Thanks a lot. Because I did post notes on this problem. Let me see. It's part of these solutions. Was that not helpful? Is it
No,
not
it was
clear?
No, it's helpful. It's very.
I look at
It's
that
just-
big table.
Yeah, it's just is that all the assumptions that we can have?
Okay,
That's
okay.
I know in
Dang.
the lecture slides. I know in the lecture slides there are some things there that are you're gonna have to consider. Like I know in this case, like obviously they didn't tell us like uniform or uniform. Or
Okay.
Laminar. Like okay, what does
Okay.
that tell us? Absolutely nothing. But like okay, well we're not supposed to like take that into consideration, or we have that in the back of our mind, but that does nothing for Navier Stokes.
Okay.
It's just like a red herring.
Okay, I will also gather these questions for professor because I told him there's like so many questions students ask me, and we have an Excel sheet now. Yeah, I know. I tried to tell him like, hey, like I'm not sure if I'm answering this right. Can you double check me and and like can you help out answer these questions? Cause dang, like are you like they should be coming to you because I am overloaded.
It's just the fact that almost nobody shows up.
To his office hours?
His office hours 3 to 4, and some people have class.
But some don't, so more people could be
don't,
coming.
And then nobody wants to wait an hour just to go to his office hours after class.
I mean, do people come to my office hours? Like 3, 4, 5?
That's 3 times more.
Okay, well, I hope I'm helping, and I hope I get good ratings.
Yeah. A good example is that a lot of these assumptions are in the lecture 16 slides.
Lecture
So you can
16.
pretty much copy it.
That's so
word.
funny.
All you have to do is take the bottom one, the red text, and then just put it all together in one page.
Lecture
And then it's
16?
very obvious. Yeah. You can take a look. It's right there. It's just,
That's hilarious.
Extremely weird because there's a lot of
That is so
algorithm
funny.
stuff, but
Thank
no-
you for that. That's hilarious.
See you.
See you. Good luck.
For these videos.
Thank you. Have a good day.
See you Wednesday or
Yeah, just email me. Have a good day. Good luck.
Take care.
Thanks.